Welcome, everyone. I'm excited to kick off today's presentation. Our topic is Unlocking Digital Logic, the Power of Boolean Algebra. We'll explore how Boolean algebra forms the foundation of digital circuits and how it empowers modern technology. Over the next few slides, we'll dive into the basics, applications, and some interesting concepts. So let's get started and unlock the power of digital logic together. Let's begin by exploring the core ideas behind mapping logic with truth tables. These tables are essential tools that help us visualize how different inputs affect the output of a logical expression. They form the foundation for simplifying complex Boolean expressions, which is where the power of Boolean laws truly comes into play. By applying these laws, we can reduce complicated expressions into simpler, more efficient forms. Next, we bring logic to life through logic gates. These are the physical implementations of our logical concepts. The fundamental operators we use are AND, OR, and NOT, which are the building blocks of digital circuits. They form the foundation of our digital future, enabling devices to process information reliably and efficiently. Moving from theory to practice, we see how Boolean algebra applies directly to real-world applications, from designing digital circuits to developing software algorithms. The power of inversion, especially through the concepts of complements and De Morgan's theorems, allows us to manipulate and simplify expressions even further. At the core of all this are variables, constants, and operations, basic elements that define the behavior of logical systems. Building on these are the associative and distributive laws, which help us organize and simplify complex expressions by grouping or distributing terms. Overall, these concepts are the building blocks of digital logic, and understanding them is crucial for advancing in the field of digital electronics and computing. Welcome, Class 12. Today, we're diving into Boolean algebra, the fundamental mathematical language that underpins all digital systems. It's the elegant system of true and false, ones and zeros, that makes our modern world possible. Boolean algebra is what allows us to design and understand the logic behind computers, digital circuits, and so much more. It simplifies complex decisions into simple true or false values, which can then be combined using various operations. As we explore this topic, you'll see how this logical foundation is essential for building the technology that we rely on every day. So, let's get started and see how Boolean algebra forms the core of digital logic. Let's start by talking about the fixed values of false, which is represented by 0, and true, which is represented by 1. These values are really the foundation of all logical operations. They serve as the basic building blocks we use to create more complex logical expressions. Next, we have constants, specifically 0 and 1, which are the fixed values I just mentioned. These constants are essential because they provide us with a stable reference point when working with logic. Moving on, the actions we perform on variables and constants are called operations. The main ones are AND, OR, and NOT. Think of these as the basic operations or tools we use to manipulate and combine logical values. They are the core building blocks for constructing logical expressions. Now, these operations act like switches. They can only be in one of two states, on or off, which correspond to 1 true or 0 false. So, whenever we perform an operation, we're essentially toggling these switches, combining simple true or false values into more complex logic. Finally, we have variables like a, b, and c. These are placeholders for values that can change, unlike constants which stay the same. Both variables and constants are fundamental because they give us the flexibility to model real-world situations and build logical expressions that can be evaluated or manipulated. All these elements, variables, constants, and operations, form what we call the core concepts of logic. They are the foundation upon which everything else in logical reasoning and digital systems is built. Let's start with the first operator, the NOT operator, or in symbols a or not sign. This operator inverts the input. So if the input is 1, the output becomes 0, and if the input is 0, the output becomes 1. Think of it like a toggle switch, flipping the state from on to off or vice versa. It's a simple but essential part of logic operations. Next, we have the OR operator, represented by the plus sign. A plus B. The key point here is that the output is 1, or true, if at least one of the inputs is 1. Imagine two switches controlling a light. If either switch is on, the light turns on. So only one needs to be active for the output to be true. Finally, there's the AND operator, shown as a B or A, and B. This operator outputs 1 only if all asterisk inputs are 1. Picture two switches. Both must be on for the light to turn on. If either switch is off, the light remains off. This operator emphasizes the necessity of all conditions being true for the outcome. These three operators, NOT, OR, and, are fundamental to understanding how logic circuits operate and are the building blocks for more complex logical functions. Boolean algebra laws are really powerful tools that help us simplify complex logical expressions. When we apply these laws, we can make digital circuits much more efficient and compact. This not only saves space, but also reduces the cost and increases the speed of the circuits. Understanding these laws is absolutely key to effective digital design because it allows us to optimize circuits and improve overall system performance. So, mastering Boolean laws is essential for creating smarter, more efficient digital systems. Let's take a look at some fundamental Boolean laws. First, the commutative law. This tells us that the order of variables doesn't matter when we're using or AND operations. So whether we write a plus B or B plus A, the result is the same. Similarly, for AND, a times B is the same as B times A. It's a key property that simplifies our expressions. Next, we have the idempotent law. This means that repeating a variable with or AND doesn't change the outcome. For example, a or A is just A, and A is also A. This helps reduce redundancy in our logic expressions. Finally, the identity law states that adding 0 or multiplying by 1 doesn't alter the value of the variable. So, a OR 0 stays A, and a AND 1 also stays A. These laws are essential because they align with what we know from regular algebra, making Boolean algebra more intuitive and easier to manipulate. Together, these laws form the foundation for simplifying and understanding Boolean expressions more effectively. Now, let's look at how these laws help us restructure and combine logical expressions, giving us more flexibility in circuit design. These are the building blocks of logic, specifically the associative and distributive laws. The associative law is all about how we group variables. Whether we group A with B first or B with C first, it's the same result. This allows us to reorganize expressions easily without changing their meaning. The distributive law, on the other hand, helps us distribute one operation over another, much like expanding or factoring expressions in algebra. These laws are fundamental because they let us simplify complex expressions and create more efficient circuits. By mastering these, we gain greater control and flexibility in designing logical systems that are both effective and optimized. This ties directly into our overall theme of building smarter, more adaptable digital circuits. Now, let's talk about the associative and distributive laws. The distributive law allows us to expand or factor expressions in a way that's quite similar to how we handle arithmetic. For example, a times the sum of B and C equals a times B plus a times C. Similarly, a plus the product of B and C equals the sum of a plus B, all multiplied by a plus C. This helps us simplify and manipulate expressions more easily. On the other hand, the associative law tells us that how we group variables doesn't change the outcome when dealing with multiple or AND operations. For instance, A plus the group B plus C is the same as a plus B. Plus C, the same goes for multiplication. A times the group B times C equals the product of a times B times C. Understanding these laws is key because they help us to reorganize and simplify logical expressions without changing their meaning. This consistency is essential as we build more complex logical statements and work towards designing accurate digital circuits. These laws are crucial for understanding how to manipulate and simplify expressions involving the NOT operator. When we apply these rules, we often find ways to reduce the complexity of our circuits, which leads to more efficient designs. Now, let's focus on the power of inversion. This includes the concept of complements and De Morgan's theorems, which are fundamental tools in our digital logic toolkit. By understanding how to invert expressions and apply these theorems, we can transform complex logic functions into simpler, more manageable forms. This not only helps in designing more optimized circuits, but also deepens our grasp of how logic operations work together. Ultimately, mastering these laws empowers us to create smarter, more efficient digital systems. Let's take a closer look at some of the key theorems that help us simplify complex logical expressions. First, we have De Morgan's theorem, which is a powerful tool for transforming logical expressions involving not, and or operations. For example, the negation of a sum, a plus b, can be rewritten as a b. Similarly, the negation of a product, a b, can be expressed as a plus b. These transformations are incredibly useful because they allow us to convert expressions into forms that are easier to analyze or implement. Next, we have the complement law. This law states that when you combine a variable with its inverse, you get a constant. Specifically, a plus a always equals 1, which means it's always true, and a always equals 0, meaning it's always false. Understanding these fundamental laws helps us simplify logical expressions efficiently and ensures that we can design reliable digital circuits. By mastering these key theorems, we're better equipped to manipulate and simplify logical expressions, which ties directly into our overall goal of designing more efficient digital systems. Logic gates are the fundamental building blocks of digital circuits. They are the electronic components that physically implement Boolean functions, transforming input signals into specific outputs. Each gate performs a particular logical operation, like and, or not, which are essential for processing information in digital systems. These gates form the core of everything from simple devices to complex computers, bringing the abstract concepts of Boolean logic to life in real hardware. Understanding how these gates work helps us see how digital circuits execute complex tasks through simple, interconnected operations. So, in essence, logic gates are what enable digital technology to function seamlessly and efficiently. Let's take a look at some of the fundamental logic gates. First, we have the NOT gate, also known as the inverter. Its primary function is to invert the input signal. So if the input is high, the output becomes low, and vice versa. It's quite straightforward but essential for creating more complex logic. Next, we have the OR gate. Its key characteristic is that it outputs high, or a 1, if any of its inputs are high. This makes it very useful when you want to check if at least one condition is true. Beyond these basic gates, there are others like XOR, NAND, and NOR gates, each with their own unique functions. For example, XOR outputs high only if an odd number of inputs are high, while NAND and NOR provide their own specific logical behaviors. Finally, the AND gate outputs high only when all inputs are high. It's the logical equivalent of an all conditions must be true scenario. All of these gates form the building blocks of digital logic, and understanding their functions helps us grasp how complex digital systems are built from simple, reliable components. Let's take a closer look at this table. It shows the basic operations for two inputs, A and B on the left. You see the possible values for A and B, either 0 or 1, and on the right the corresponding output for each combination. For example, when both A and B are 0, the output is 0. When A is 0 and B is 1, the output is 1. Similarly, if A is 1 and B is 0, the output is 1, and when both are 1, the output remains 1. This kind of table is called a truth table, and it systematically lists all the possible input combinations for a Boolean expression or logic gate. The key point here is that truth tables help us verify and understand how digital circuits behave. They provide a clear, organized way to see how different inputs influence the output, which is essential when designing or troubleshooting digital systems. So, in essence, truth tables are foundational tools that help us map out and confirm the logic behind digital operations, ensuring everything functions as intended within our circuits. Boolean algebra is not just an abstract concept. It really forms the backbone of almost every digital device we rely on today. From the simplest calculator to the most complex supercomputer, the principles of Boolean algebra are at work behind the scenes. It's the foundation that makes digital logic possible. When we move from theory to reality, Boolean algebra finds its true power in real-world applications. It's what allows us to design and optimize digital circuits, automate processes, and ensure reliable data processing. So, understanding these applications helps us see how these concepts are not just academic, they're essential to the technology we use every day. Used in robotics, industrial control systems, and automated machinery to make decisions. When we talk about automation and control, Boolean logic plays a crucial role because it helps machines determine the right actions to take. Every operation inside a CPU, from performing arithmetic calculations to executing logical comparisons, relies on Boolean logic. It's essentially the foundation of how computers process information. The primary application of Boolean logic is in designing computer processors. It allows engineers to create hardware that is both efficient and reliable, ensuring that computers can perform complex tasks quickly and accurately. Digital circuit design is another key area where Boolean logic is essential. By using these logical principles, engineers can build circuits that perform specific functions, enabling the entire digital infrastructure we depend on every day. So, in summary, Boolean logic is at the core of many technological innovations, especially in areas like robotics and hardware design. It helps us create smarter, more dependable systems that drive modern automation forward. Keep exploring, keep questioning, and continue to build your understanding of the incredible world of computer science. The power of Boolean algebra lies in its ability to translate complex logic into simple, manageable operations, forming the invisible language of every digital device. Boolean algebra, with its elegant simplicity, provides the mathematical framework for understanding and building the digital world. By mastering its concepts, you gain insight into how computers think and process information. This foundation is essential because it underpins all the technology we rely on daily. As we look to the future, remember that understanding these core principles is key to shaping the digital innovations ahead. This is truly the foundation of our digital future.